A super important part of machine learning is what's called model selection, and a tool for thinking about model selection is the bias-variance decomposition. The bias-variance decomposition, and it's almost a trivial identity, but it's extremely handy for thinking about this. So what is it? The bias-variance decomposition, in a nutshell, it says that the mean squared error, the MSE, equals the bias squared plus the variance. That is the bias-variance decomposition. And now you might say, what is this MSE thing? You haven't defined the MSE. And so let's define it. The mean squared error, MSE, of an estimator, theta hat, and remember an estimator is always some function of the data. So we're thinking of random data, so this is a random variable, an estimator for some parameter theta, and it is, we write it MSE of theta hat, and it's the expected value of theta. I'll put theta hat minus theta squared, and I'll put given theta to emphasize that we're not averaging over theta here. We have no distribution over theta. We're just averaging over the data. So this you may recognize as this is just the risk R for the parameter theta and the decision rule F, or the estimator function F. Oh, and it's the risk of that under, so this is using under square loss. When the loss function is the square of the difference. So that's all the MSE is. It's the mean of the squared error. Natural enough. Okay, now let's recall, in order to introduce this proposition, just to remind you here, the definition of the bias of an estimator, the bias of theta hat, is just its expected value minus the true value of the parameter that it is intending to estimate. And now we're ready for the theorem, or the proposition. It's not really, I guess, a theorem. It's maybe just a proposition. A proposition, the bias-variance decomposition. I'll just write it here a little more explicitly. The mean squared error for any estimator theta hat is the bias theta hat squared plus the variance of theta hat. And theta hat is a random variable, so it's the variance of that random variable. So let's prove this. It's really simple to prove, actually. Well, let's just write out. I'm going to drop the conditioning on theta, so you just to clean things up a little bit, simplify the notation slightly. So it's the expected value of this difference. So it's just the expected value over the data, not over theta, just to be clear. And let's introduce mu to be the expected value of theta hat. So we're gonna define that, and now we'll just add and subtract it. Actually, mu minus theta. We can always do that. And let's put some parentheses in there. And let's square this out. So continuing this here on this line, we're just going to square these. So it's theta hat minus mu squared plus 2 times the product, theta hat minus mu minus theta, plus mu minus theta squared. Just a little simple algebra. And now the expectation moves through, so we get the expected value of theta hat minus mu squared plus, now here, theta is a constant. Remember, theta is not random. Mu is a constant. And so this is just the expected, so when we move the expectation through, we get the expected value of theta hat minus mu times this other stuff, 2 times mu minus theta. And this is because, well, right, I guess we just have it right here. The expected value of theta hat equals mu, so this is just 0. So the middle term just drops out completely, and we get the expected value of the first term plus the expected value of the second, or of the last term. And this last term, theta is a constant, mu is a constant, so this is just the expected value of a constant is that constant. And what's this? This is theta hat. Mu is the expected value of theta hat. So this is just the definition of the variance of theta hat. So this is the variance. So this is variance of theta hat. And what is this? Mu is the expected value of theta hat. And theta is the value that it's trying to estimate. So this is just, if I flip these around, I could flip them because of the square. This is just the bias squared, right? It's just that. So we get the result. I'll flip them around just to make it look like this. And it's just super simple. Easy thing to prove. You just basically add and subtract mu and multiply stuff out, and you get it. So it's almost a trivial fact, but it's a nice, very nice sort of way to decompose the mean squared error. And oftentimes oftentimes a parameter will be a real valued thing. And so this is oftentimes a natural measure of your estimate. A natural way to measure the error of your estimate is using the mean squared error, just using the square laws. Now let me give you a little example just to illustrate this. I think you probably think it's fairly obvious by now, but let me give you just a silly example. Silly example. Just a super simple example to illustrate this. Let's say that we have some random variable x, which is normally distributed, a univariate normal with mean theta and variance 1. And here theta is going to be non-random. We're not putting any distribution on it. And it's unknown. And our data in this little example will just be the single value x. So it's sort of like n equals 1. Our data is just x. And now let's say we wanted to estimate theta. Well, maybe the natural thing to do, I'll put in quotes, natural estimate, the thing that might occur to you first would just be, let's call it delta. Let's start using delta for a decision rule. Delta of 1, or delta sub 1 of our data would just be x, right? That's the sample mean for our data. So that's a very natural thing to do. And the bias here, well, it's unbiased, right? Because, well, we already saw that the sample mean is unbiased. The expected value of x is theta. So the bias is 0. And the variance, what is the variance? The variance is the expected value of x. Well, x is distributed with this distribution. So the variance of x, well, the variance of this random variable, delta 1 of d, is just the variance of x, and that's just 1. So that's easy enough. So the MSE is 1. Simple. And now we'll do the silly estimate of theta. And what is the silly estimate of theta? Let's always estimate theta to be 0. Kind of a silly thing to do, but let's see what happens here. This will be an interesting example to illustrate something in upcoming videos. The bias is going to be theta squared, because remember, the bias is the difference, or the bias squared, I should say. I could put a square here too, is theta squared. The bias is the difference between the estimator, or the expected value of the estimator, and the true value. The expected value of 0 is 0, of course, and the true value is theta, so the bias squared is theta squared. The variance, what is the variance? The variance of this is just a constant, right? So the variance is 0. And so the MSE is theta squared. So I wanted to give you this little example because so here the bias was 0. This was an unbiased thing, but we did get some variance. We could make that, whereas in the silly example, we could always just draw down the variance to 0, have no variance, but then we incur a pretty hefty potential bias here. Depends on what theta ends up being, but theta, I mean the bias squared could be quite large. So I think this is probably natural. I mean, this is probably obvious enough why this would not do well, but it just illustrates this sort of decomposition in a very easy to understand case. Now, an interesting question that might arise from this, that might occur to you, is you might say, now this natural estimate had 0 bias. I wonder if there's a way to introduce a little bit of bias and reduce our variance by more than we increase the bias. So could we reduce our mean squared error here by allowing for a little bit of bias, but getting a big decrease in variance so that we could reduce the overall mean squared error? And that leads you down a very interesting path. A very interesting path toward things like shrinkage, what's called shrinkage, and Stein's paradox, which is a very, very astonishing result, a stunning result. Stein's paradox, I'll leave that as a sort of cliffhanger. Stein's paradox is a very surprising result, which says that, not in this case, but at least in a little bit, so in like at least 3 dimensions in Rn, this sort of example, if you have a multi-dimensional Gaussian, it turns out that the natural estimate, that is the sample mean, is inadmissible. It's inadmissible, which is very surprising. We'll talk more about inadmissibility and admissibility in a little bit. Okay, see you soon.